Hi, and welcome to 5.4 Kinetic Friction and Slowing Down. In this video, we'll be doing some critical thinking type questions, and it's very important that you try them on your own first. Keep trying. Don't just try once. Look at the problem. Stop. Come back to it. Rack your brain. Try to figure it out for yourself. By watching me do it, you're not really helping yourself as much. But if you've gotten to the point where you feel like, oh, okay, I need to look at the video for real help, then, by all means, watch this video. Number one, a different force is applied to each of 4 1 kilogram blocks to slide them across a uniform steel surface at constant speed, as shown below. This is an important fact, that it's constant speed. Why is that important? Because that means it's not accelerating. The acceleration is 0, and if the acceleration is 0, the net force is 0 newtons, meaning that the forces are balanced. So if you draw your free body diagram and they're pushing the block to the right, the frictional force is balanced out by that because it's moving at constant speed. So all of these forces, even though they're technically the applied force, is equal in magnitude to the frictional force. So these are all really, you could think of them as the frictional force. But technically they're still the applied force. So now we know what the frictional force for each one is. And we know the mass. The mass for all of them is the same. And if the mass is the same, the weight is the same. Fg equals mg. And in this case, if the weights are all the same, the force due to gravity, that means the normal forces are also identical, equal in magnitude, opposite in direction. So what does that tell us? That tells us that we don't have to worry about, if we're looking at our frictional force formula, the fun formula, this is staying the same. The normal force stays the same. The frictional force is the things that's changing. It's 5, then it's 2, then it's 3, then it's 4. All right? Now, since the frictional force is changing, how's that going to affect the coefficient of friction? Right? They're asking, in which diagram is the coefficient of friction between the block and the steel the smallest? And you might be thinking to yourself, oh, coefficient of friction, let me look in my handy reference table. But the thing they don't tell you is these blocks are all made of different materials, and they don't tell you what the material is. So you can't look in your reference table and determine the coefficient of friction. So how the heck do you do that? It's all about the formula. And you don't technically have to calculate the coefficient for each situation, but you could. All right, if Fg is equal to mg, and each one is 1 kilogram, they make it easy for you. So it's 1 times 9.8 meters per second squared. So the weight of each block is 9.8 newtons. So that's easy. So every time you plug in a 9.8 newtons here, and this is the coefficient, and you just plug it. Okay, first it's 5, then it's 2. All right. Technically, even though I like to use the FF equals mu Fn formula because it's on the reference table, you guys should really know the coefficient of friction is just the ratio to the frictional force to the normal force. And we found that by, dividing both sides by Fn. I know this is a long explanation for this problem, but there's a lot of good stuff packed away inside of it. So I'm taking my time with it. I don't really care. You can calculate each one. Just do 5 divided by 9.8, 2 divided by 9.8, and you'll quickly see the relationship. All right? The relationship between the frictional force and the coefficient of friction is direct. It's a direct relationship, and we could tell right away because of this version of the formula. It's a useful version, even though it's not on the reference table. So what's happening is, for A, that's the biggest force, so that's going to be the biggest coefficient of friction, meaning in this situation, it's the roughest material. Remember, all the blocks are different types of material. The surface is steel, and it looks like everything's steel, but the blocks are different materials. And, so I think you get the point now. It's a direct relationship, so this is the greatest, and 2 is the smallest number here. So that's going to give you the smallest coefficient of friction. Okay? The other 2, 3, and 4, they're in between. All right, moving on. That was a good one. I had a lot of fun with that one. Moving on. Number 2. A 0.7 kilogram block sliding on a horizontal shuffleboard court is slowed to rest by a frictional force of 2.1 newtons. What is the coefficient of kinetic friction between the puck and the surface of the shuffleboard court? This is almost identical to the problem we did in class, but we could do it again. Or you could look back in your notes and try to figure it out on your own. You know what? Before we write the givens, I always like to draw our free body diagram because it's important in this case. You really have to think about what forces are acting on it. It's not always this same diagram. Each situation is slightly different. But we're on Earth, so we know we have a weight, and we're on a surface. The puck is on the surface of the shuffleboard court, and it's a horizontal surface. So the normal force is acting straight up. And in this case, again, it's equal to the weight, which is nice. Makes our job a little easier. Now let's see. It's sliding along the court, and it's slowed to rest. It doesn't say it's being pushed by anything. So you know what? I am not going to draw this applied force. Nope. There is no applied force in this problem. But it is being slowed down. So even though the velocity is going in this direction, all right, or we could choose what direction, it doesn't say. So I always think of it as going to the right. Personally, you could choose any direction as long as you're careful with your signs. All right, so let's assume the velocity is going to the right. The frictional force acts to the left, FF. And what type of friction is this? Is it static or kinetic? Static or kinetic? Think about it. It's sliding, so it is kinetic. All right, so kinetic friction, boom. Look in your reference table, right? It's asking for the coefficient. Okay, where's shuffleboard and puck? It's not there. You could look as hard as you want. It's not there. So you know what we have to do? We have to improvise, adapt, and overcome. Look at the things that they give you and try to figure out a different way to find the coefficient besides just looking in the reference table. So let's write down, we did a good diagram, that's only half the battle. Let's write down the other information they tell us. The mass is 0.7 kilograms, okay? And it's being slowed to rest by a frictional force of 2.1 newtons. How nice of them. They're telling us flat out what the frictional force is, 2.1 newtons. That is interesting. It's hard to draw I should draw my diagram a little bit bigger next time. That's fine. It's saying what is the coefficient of kinetic friction. Yes, it's not in the reference table, but there's an equation within it. All right, we could do, you know what? We could do this equation here. But again, I always refer to the equations that are in the reference table, just so, it's always the same for you guys. FF equals mu Fn. Okay? And in this case, it's the kinetic coefficient of friction. Yes, we don't know what this is, but that's okay. That's what they're looking for. We must know everything else in that equation. And we do. They tell us flat out the frictional force is 2.1 newtons. And we can assume that we're on Earth, negative 9.8 meters per second squared. Why am I writing that? Because if we know what the weight is, we know what the normal force is, and then boom, we know everything else that's in that equation. We're going to solve for mu k and plug in a number right here. But first we got to solve for the normal force. So Fg is equal to mg. Fg is equal to 0.7 kilograms times negative 9.8 meters per second squared, or newtons per kilogram, whatever you please. And you get 6.86 newtons, or we could round it 6.9 newtons down, negative. So this is 6.9 newtons down. That means this is 6.9 newtons up. And there is the rest of our formula. Now we can solve for the coefficient of friction. We did not need to look at the front of the reference table at all. So you do 2.1 divided by 6.9, and you get 0.304, blah, blah, blah. What are the units for the coefficient of friction, you ask? There are no units, because if you look at the formula up above here, all right, you got a newton divided by a newton, a force divided by a force. Those newtons cancel out. That's why there's no units for the coefficient of friction, And we could just leave it like that. Okay, number 3. A 1,250 kilogram car is traveling at a constant velocity of 20 meters per second on a dry concrete street. The driver of the car sees Phil the Physics Squirrel 31 meters away and suddenly slams on his brakes, causing him to skid to a stop. I hope Phil the Physics Squirrel is okay, but I don't know. Is he going to stop in time? The suspense is killing me. All right. It says, what is the frictional force acting on the car? So same situation, it's the same process every time. You want to start by drawing yourself a nice picture, a free body diagram. We have the weight of the car, and it's on the road, so we have the normal force pushing back up. Now, this maniac isn't stepping on the pedal. There is no applied force pushing him forward. If we assume he's going to the right, that means the frictional force is the only force acting in the x direction. That is slowing him down. And he's sliding. He's skidding along the road. So that's going to be FFK. It's not static friction because he's not stopped. He's sliding. We hope he stops in time, but let's see. All right, what is the frictional force? Well, we know the mass is 1250 kilograms. We assume we're on Earth. We're not on planet X. This is not an alien squirrel. The velocity is 20 meters per second. We're not going to really need to know that yet. Technically, that's the initial velocity. We know he's even coming to a stop, so VF is equal to 0 meters per second. We know that too. So let's see. How are we going to do this? Well, it's asking for the frictional force specifically. So again, we want to try to do this formula, FF equals mu Fn. It's a lot of fun, and it's kinetic. So let's see. What can we plug in? FF equals the coefficient. It's a car, so that's rubber. It's not a rubber car, but there's rubber tires, right? And it's on dry concrete. So we look in our handy reference table. Boom shakalaka. And where is it? Rubber on concrete, dry. It's the first one. Now you got to ask yourself, am I going to use kinetic or static? Again, it's not stationary. Nope. It is sliding. It's kinetic. So we use 0.68. 0.68. That's the coefficient of friction. And we write it in right here. What the heck is the normal force? We don't even know yet, but we know the mass. So we could find Fg. So Fg is equal to the mass times the gravitational field strength. Fg is equal to 1250 times negative 9.8. Let me call it newtons per kilogram since I just said gravitational field strength. Doesn't matter. All right, so let's see. 1250 times negative 9.8. 12,250 newtons in the negative direction. That's a big force, but it's the weight of a car. So, that's to be expected that it would be a big force. 12,250. So the normal force is 12,250. So we plug in 12,250 over here. You do the multiplication. The frictional force is 8,330 newtons. Now, it's important to note that this is really just the magnitude of the frictional force. Yeah, you get a positive number, but that's just because, in this case, it doesn't tell us what direction the car was going. We chose to make the car traveling to the right, meaning the frictional force would be pointing to the left. So some of my students are always like, well, why don't you get a negative number for the frictional force? It's pointing to the left. Well, we just chose arbitrarily to make it pointing to the left. If it told us that the car was traveling to the left, we would do it differently. Well, actually, you still get a positive number, but then you choose to make the positive or negative sign depending on how you drew your diagram. So this formula will pop out the it'll pop out the magnitude, not the direction. Unlike this one, the net force acting on the car, right? So when we're calculating the net force, we could do F equals ma, sure, but we don't know what the acceleration is. Oh, yeah, we know the velocity. We know the change in velocity, but it doesn't say how long, how many seconds it takes to slow down to a stop. So we can't figure out what the acceleration is. We need to figure out a different formula to use. By definition, the net force is the sum of all the forces. So in the y direction, we could say it's Fn plus Fg. This is positive 12, 250, plus negative 12, 250. And as you could see, the net force in the y direction is 0, which is a good thing because we don't want to accelerate through the ground, or we don't want to be thrown off the ground. So that's in the y direction. Let's look in the x direction. In the x direction, look at all these forces we have. Oh, it's only one force in the x direction. So the net force must be equal to the sum of all these forces we have in the x direction. It's only one of them. So the net force is equal to the frictional force, 8,330 newtons. And the way we drew this, we drew the force of friction pointing to the left. By convention, we should make that negative, because that's going to help us calculate the acceleration of the car. We made both our velocities positive, and we are hoping that we slow down, so we should get a negative acceleration so that Phil the physics squirrel doesn't die. As I said before, there's not enough information to use a kinematic equation. We don't know what the time is. So we need a different way to find the acceleration. Let's think dynamics. We know the net force is equal to ma. If we're looking for the acceleration, I might make my life a little bit easier and use this version of Newton's second law. A is equal to the net force divided by the mass. So the acceleration is equal to negative 830, 8,330 newtons divided by the mass, which they tell you is 1,250 kilograms. So the acceleration of the car is negative 6 point, you could round it to 6.7 meters per second squared. Again, the velocity is positive, the way we drew it. It's going to the right. The acceleration is negative. It's going to the left. That means that we're slowing down when they're going in opposite directions, which is good because, again, Phil, his life is in danger. How far does the car skid? Does the car hit Phil the physics squirrel? I can't even, I'm too nervous to even do this problem, but let's do it. Let's see. The initial velocity is 20 meters per second. VF is 0 meters per second. A is negative 6.7 meters per second squared. And we have 3 pieces of information now. That's enough to find the distance. So we look in our reference table. We want an equation that does not have t in it. Who cares about t? They're not asking for it. We don't have it. Let's find an equation that doesn't have t. Look in the back of your reference table. Think back to all those days we did kinematic equations. Let's see. This has t in it. Nope. This has t. Where's the t in this one? I don't see one, so let's use it. VF squared is equal to VI squared plus 2AD. I am sorry for not giving you enough room on this sheet. So 0 is equal to 20 squared plus 2 times negative 6.7. If you don't put that negative in, you're going to get a different answer. And I'm thinking that Phil's going to die if you do it. And, don't make Phil the physics squirrel die by making that a positive number, people. All right, the negative sign matters. So you do that math, and the distance, the displacement is equal to, you get about 30 meters. That's only 1 meter away from Phil, but don't worry, Phil the physics squirrel survives this day if you did the math right. All right, number 4. Is this the last one? Hey, look at that. The main event. A student and the wax skis he is wearing have a combined weight of 735 newtons. The skier travels down a snow-covered hill and then glides to the east across a snow-covered horizontal surface. So if you can't picture really what's going on here, there's a hill covered with snow, and then there's a horizontal surface. The skier Very hastily drawn skier with a hat, then skis and pulls. All right, there's the skier. They're going to go down the hill. They're picking up speed, but now they have some velocity. And they just continue moving with that velocity. They're not push. It doesn't say they're like pushing themselves forward with the poles. Okay, they have this velocity and they're coasting. They're maxing and relaxing. Skiing is really fun if you've never done it before. Try it out. All right. So you have this situation. We're not really looking at this part. We're only looking at this part here. All right, it says, what is the magnitude of the force of friction acting on the skis as the skier glides across the snow-covered horizontal surface? So let's get rid of this and draw a free body diagram. All right, so now here's our skier, and the skier is on Earth, so there's a force due to gravity. They're standing on a surface, so there's a normal force. I mean, they're standing up straight, but the skis are gliding across them. So if your velocity is going to the right, like we had in our previous picture, the frictional force is opposing them. And again, there's no applied force. Common theme for this problem. So it says, what is the magnitude of the force of friction acting on the skis? Let's see what else they give you. Oh, they say that. Is that the mass? Do you have to do Fg is equal to mg? Fg is equal to 735 newtons? Newton? That's not the mass, people. They're telling you straight out what the force due to gravity is. You do not need to do an equation. Don't get into autopilot, all right? They tell you right away that's 735 newtons. I'm not going to even write it over there. I'll just write it straight in my free body diagram. 735 newtons. Boom. I wonder what the normal force is. 735 newtons. Not 735 times 9.8. That would be a crazy heavy skier. So let's see. The frictional force. Now we could go straight to the equation. Isn't that nice of them? It took them this long to give you just a straightforward equation like this. The frictional force is equal to the coefficient of friction. Oh man, I hope this is in the reference table. Let's see. Does it say, yep, waxed skis. Okay, waxed skis on snow. Let's see, waxed skis on snow. Gone back to the first page now. And, oh, nice. All right, is it static or kinetic? It says they're gliding, so it's kinetic. 0.05. 0.05. That's not a very big coefficient of friction. It's not a rough surface. It's pretty slick. This person's just living life right now, enjoying the great outdoors on a pair of wax skis. Can't beat it. So the frictional force, by the way, it's kinetic. You don't have to write the K in, but I do. Makes it look cool. All right, so 0.05 times 735. Thought I made a mistake, didn't you? You get 36.75.8 newtons. And, you know, the way we drew it, pointing to the left. That's fine. All right, B. What is the net force acting on the skier? Same thing as above. If you're looking in the x direction, there's only one force in the x direction. So the total force in the x direction is equal to that force. It's equal to 36.8 newtons. This question isn't here to be like, oh, do another calculation. This is a scaffolding question so that you could do the next part. Next time, if you'd like, I could just ask you, what is the acceleration of the skier? Okay, you know the frictional force? What's their acceleration? They seem unrelated, but they are, because the net force is equal to the net force is equal to the frictional force. So you could just use Newton's second law now. The net force divided by the mass. It's equal in magnitude to the frictional force. And it's actually in the same direction as the frictional force. And the way we drew it was pointing to the left. The mass of the skier, oh man. Did I tell you the mass? Can we write in 735? No, because that's in newtons. It was convenient before, but now it's not. We need to figure out what the mass is first. You got to do FG is equal to MG. FG. Oh, no. See? I'm in autopilot. They tell you FG. 735 newtons is equal to the mass times negative 9.8 meters per second squared. And if I did it like this, I'd get a negative number for the mass. So what am I missing? Well, FG is pointing down, isn't it? So you make that negative. That's how you get a positive number for the mass. Mass is a scalar, so it should be positive. You get 75 kilograms. That's a reasonable mass. All right, 75 kilograms. Underneath that 36.8 newtons, your acceleration is going to be about 0.5 meters per second squared in the direction of your frictional force. The way we drew it, it was pointing to the left, negative. All right, D. If the skier has a speed of 5 meters per second at the bottom of the hill, right before they started decelerating, how much time does it take before the skier glides to a stop? Assume the skier does not use their poles to push ahead. Again, just a kinematic equation here. They're telling you the initial velocity. We just did all that work to find the acceleration. 0.5 meters per second squared. There must be something else. They're asking for the displacement, and I don't see any numbers. Give up. Go home. No. There's a piece of hidden info right here. You're coming to a stop. So what does that tell you? That's right. VF is equal to 0 meters per second. And you're looking for how much time does it take? How long? I'm going to think probably a long time. I mean, 5 meters per second isn't that fast, but you're on snow, so you're going to be gliding for a while, I would assume. Let's see. All right, so what don't we care about? Don't care about that displacement. So you could just do, a couple different options. VF equals VI plus AT is a good one. 0 is equal to 5 plus negative 0.5 times T. So you get negative 5 is equal to negative 0.5 T. So T is equal to 10 seconds. That's a pretty decent amount of time. Imagine you're the skier here. You're skiing along. Okay, you got your hat, nice and cozy and warm, enjoying the sights, enjoying the silence. All right, yeah, very nice. And now I want you to imagine yourself, you're traveling along for 10 whole seconds. Have a good day and enjoy the skiing for 10 seconds. Beautiful. It was beautiful.